Hi everyone, Sim here. For starters, I'm just going to show you what all the code that you will see in this video does.
Here, the robot is running at 0.1 Hz for 10 seconds, then it's going to run at 0.5 Hz for 2 seconds, then 1 Hz for 1 second, and then 2 Hz for 0.5 seconds, then 3.3 Hz for 0.3 seconds, and finally 5 Hz for 0.2 seconds.
Hello, I'm Tommy. I'm just going to walk you through some code for our project. We have three functions that we continuously call back on in our main function. The first one is centralize, which we use to turn the servo back to its center position. The second is the 20 millisecond clock, and the third is called pause edge. This function is used to allow the servo to detect when a pulse is being sent to it. For the main function, we have a clock running in a different cog, and to start out, we have a loop pulsing out the centered function position, incrementing by 1, 5, 10, 20, 33, and 50. To replicate their respective frequencies. Through experimentation, we found the values that each frequency must increment through to get an accurate period. Inside the for loops is the algorithm to get the sinusoidal motion of the servo mechanism. We first call back on the function positive edge to detect when a pulse is being sent to the servo, and after the microcontroller detects the pulse, it runs a sign statement that will incrementally push out new values for the servo to run at, with the center position being its initial position.
Was 0.1 hertz. So now we're going to run him at 0.5 hertz. So that would be 5. Since there are no decimals in Blockly prop, we gotta use whole integers. So that was 1 hertz. Now we're going to do 2 hertz, which is 20. Run that. 3.3 hertz, which is 33. Run that. And then our final will be 5 hertz, which will be 50. At the higher frequencies, it's not able to sweep all the way back and forth. That's because it's running faster than the motor can handle.
I'm going to be teaching you how to find the frequency response of a servo, and from that, create a bode plot. Frequency response can give us very insightful information on how fast we can drive the servo. One way of representing the frequency response is by creating a bode plot. A bode plot is a graphical way of showing the magnitude of the system in respect to the frequency. How do we create a bode plot? We need to do an experiment. We need to find the magnitude response of the system at various frequencies. We're going to make the servo point from minus 90 degrees to positive 90 degrees. We can find the magnitude response of the servo by measuring the output angle over the input angle. We have to do this at different frequencies. I have listed the frequencies that we're going to be doing today. In order to go smoothly from positive 90 degrees to negative 90 degrees, we will use the sine function. Because the clock goes from a high signal to a low signal, we were able to get 428 points in 10 milliseconds. We take the total amount of time, which is the 10 milliseconds, and we divide that by the total amount of points within that 20 milliseconds. So the microprocessor board can measure each point in about approximately every 234 microseconds. Put the sine function in a new processor so that the clock and the sine function is running at the same time. Then detect a positive edge, take how many ones and zeros, highs or lows there are, and we keep on doing that until our variable, which is value, becomes not zero. Now that will become not zero after the sine function completes. Print out all the data so that we can see how many ones and zeros there are. And the amount of ones and zeros will tell us how long the sine function took. We can times the seconds per point number by the number of points for a sine, which is 790, and that'll give us the total amount of time that it took the sine function to go from 0 to 360 degrees. The easiest way to get a good reading on this is recording the robot's angle response. Having Excel plot the frequency to the magnitude ratio gives us our bode plot.